So, hi everyone, I am Massinissa Hamidi, and this work studies strategies for reducing the biases that stem from the sensor's position in IoT deployments. So here we consider on-body sensor deployments, so sensors placed in different places on the body, for example, the hand, the hips, the torso, so on and so forth, each position providing a particular perspective of the phenomenon being considered. So here, obviously, we consider human activities. The goal of this work is to properly fuse between all these perspectives by reducing the main bottleneck, which is the bias induced by the sensor's position. So the fundamental idea that we will present in the following is that there exists components in the sensory signals which are universal and unbiased that can be fused and mixed together, whatever position they originate from. And on the contrary, there are other components which are specific to the position of the sensor they originate from and which cannot be mixed with other sources. So to start with, we will provide small background on activity recognition, and then we will dig into the proposed approach. So formally, what we consider here is a collection of M sensors located at positions P1 through PM of the body, obviously. And each sensor generates a stream of observations of a certain modality, such as accelerometer, gravity, magnetometer, so on and so forth. So here you can see an example of data from an accelerometer that describes the range of motion along the three axes of the Cartesian reference frame or coordinate system. And typically, the processing of such data begins with a segmentation step in which the potentially infinite sensory stream is broken up into frames of a certain size. So not too small so as not to miss important patterns of motion, and not too large so as not to induce noise to the process. So after this, we generally cast the problem of activity recognition to a problem of sequence classification with, for example, neural networks or any other methods that is based on the extraction of relevant characteristics from the input sensory signals. Here we have an example of a network in which the hand-specific circuit performs, let's say, projection or transformation from the segmented raw sensory inputs generated by the hand sensors, in this case, towards a latent space in which the separation between the different activities is feasible or is easy. So in other words, for each segmented sensory input or frames, the circuit gives a representation or a point in the latent space. What we have seen here is a circuit that only processes data from a single position, a hand, as we saw, but the principle can be extended to data from the other positions, so the torso, back, and hips. And the difference here is that we add a fusion layer based, for example, on the concatenation of the learned representations specific to each position. So we can also use much more advanced approaches for the fusion, such as representation alignment, based, for example, on canonical correlation, as you can see here. So the learning is done in joint fashion, so end-to-end, since such layers are end-to-end differentiable. Well, with these kinds of approaches that essentially flatten the data, so the data is flattened and the position is not considered properly, one can face a problem where the learned transformations produce entangled latent spaces, so that you can see here on the figure, and which do not help in correctly separating the target classes. And the reason is that these different views naturally induce noise. So in other words, different views do not convey necessarily information of the same nature. And in standard learning configurations, the noise is unfortunately not without consequences. This problem is typically related to the bias that is induced by the position of the sensors. And hence, we need to consider properly this multitude of perspectives and take into account properly the position bias, the position bias that is induced by the exact location of the sensor. So this is the problem we are dealing with in our paper, and we propose for this to abstract away the bias that is induced by the sensor's position. As we said previously, different views do not convey necessarily information of the same nature. And to make this fundamental idea more concrete, let's consider, for example, the activity walking or running. Well, we can see that the motion data generated by the sensors located at the level of the hand or the hips are made up of translational components. So in other words, the displacement of the body relatively to the environment, to the whole environment, and other components which are cyclic by nature and which correspond to the displacement of the hand or the hips relatively to the reference, which is the human body. So we have two types of data. One is that captures the motion relative to the environment, to the whole environment, so translational data, and other types of data which are cyclic and which are relative to the human body reference. Okay, so the cycle is performed relative to the body. Okay, and in this configuration that I described right now, discriminating between walking and running can be based, obviously, simply on the translational components. So the ones that are based on the entire environment. So walking is the pace of walking is largely smaller than the pace of running. Okay. And why the distinction between running and cycling, for example, can be done using the cyclic component. Why? Because the hand remains relatively static on the bike. Okay. So as indicated previously, the fundamental idea behind our approach is that there are components of the signal which are specific to the positions, which are not mutualizable, and others, so-called universal components, which on the contrary are mutualizable, can be fused together. Okay, so these can correspond to the different types of motions that I described previously. So our goal is to build a transformation able to perform such separation. So to separate the different types of data or different types of information that are inside the data. Now, the main issue now is to put in place a mechanism that can, from the data streams, build a representation capable of encoding in a very precise manner the position-specific components, and in the other part, the universal components. So how can we manage to separate these signals, and how can we make each component of the representation correspond to exactly these two types of components that I described? Well, several works exist in the literature and have recently dealt with this problem of decomposition with the so-called disentanglement approaches. And for example, this work noticeably sets up data sets dedicated to the evaluation of such approaches. That, for example, here we can see the moving Massinissa or the disprites. And these data sets consist of, as you can see, basic patterns So like digits from 0 to 9 in the case of the moving mist, and the shapes such as hearts, squares, circles in the case of these sprites on the right figure. And the specificity of these data sets is that they encode, in addition to these basic patterns, variational factors such as the position of these patterns in the image. You can have also the rotation of these patterns, of these forms, and their scales, so on and so forth. Okay, and it is precisely these variation factors that the disentanglement approaches try to learn, in addition to the pattern itself. Okay, and to go very rapidly in this literature, you have actually some approaches that use explicit separation, for example, by saying that there are separated components of the latent space. Actually, the representation is decomposed at the origin. And you have other methods that try to separate or decompose in actually an implicit manner, okay, by providing featured objective functions like the beta VAE here, which tries to build sparse representations. Okay. And you have also other methods, more featured methods, such as this one, which was presented in the ICL 2019, and which provide, in addition to the beta VAE objective function, another term which impose a certain structure in the latent space. Okay, so here I will come back to these details if you want, but for now, let's dig to the framework that we propose, which is obviously based on a federated learning-like process, where we have multi-level processing. Okay, so the first, at the local level, for each position of the deployment, there is a learner who is in charge of carrying out the decomposition of the signal with the method that we presented previously. Okay, so it decomposes the signal with, as a result, components of the latent representation which must correspond to the specific position-specific data, and other which must correspond to the universal components. The local learner's objective can be formalized as the empirical risk of the distribution of the data that is specific to the position. Okay, so we don't have the same distribution, but there are different distribution depending on the position of the sensor. And after the local learner learns, try to decompose the signal, there's a central level where a reconciliation is carried out between the different perspectives, with an aggregation of the weights of the local learners from each of the position considered. Okay, so this aggregation is weighted with weights which can themselves be learned, and the problem that can arise here is the divergence of the weights of the learners. Okay, so here the idea is that the local learners try to decompose the different components of the data, and then the universal components have to be conciliated together. Okay, the specific components have to remain specific to the positions. However, the universal components have to be conciliated together. We have to converge to a unique, unbiased, universal representation, let's say. Okay, so what we propose here to deal with this divergence, this problem of divergence between the local learners, is to impose a regularization term. So we impose that the universal components that are learned at each local learner have to be the same at the end of the day. Okay, so for this we propose this the objective that you can see here, and which is carried out with can be implemented via conciliation correlation-based representation alignment techniques. Okay. So the end-to-end process begins with, to sum up actually, the end-to-end process begins with the initialization of the referential learners' weights. Okay, you can see here highlighted in red, which are then distributed to the local learners. This is the beginning of the process. So the local learners independently performs several stochastic gradient descent iterations to optimize their own objective function. So here depicted in black arrows. And at the end of these iterations, we proceed to the conciliation phase. So reconciliation takes place, as we have seen previously, through a weighted aggregation of the weights of different local learners. And here you can see how the central weights are updated using the gradient steps that are aggregated from the local learners. Okay, so this brings us to the experimental part of our contribution, where the empirical evaluation is organized into 3 axes. We first evaluate the quality of the data decomposition process. Then we compare our model against state-of-the-art activity recognition models in terms of classification performances. And finally, we evaluate the proposed model within different inference configurations. And I will dig to it in one moment here. So before that, here is the experimental setup. We evaluate our approach on human activity recognition task. And we use for that the SHL dataset, which provides multi-model and multi-location data recorded in real-life settings. And among the considered activities, we have, for example, still, walking, running, so on and so forth. For comparison, we also evaluate our approach on 2 additional representative datasets, the heterogeneity R dataset and fusion dataset. For reference, obtained results are compared against various baselines from human activity recognition literature, for example, deep conval STM, deep sense, and attention sense. And we also compare against custom baselines. We use for the evaluation meta-segmented cross-validation to alleviate the problem of performance overestimation, and F1 score is used to measure the performances. So we start with the evaluation of the data decomposition process, and we were able actually to implement this model with a variational autoencoder that you can see here, based on LSTM-like recurrent layers, in order to typically model the temporal dependencies of the data. Okay, we can see here the evolution of the components of the latent representation between one phase of conciliation and another, with each time axis of the representation which are activated. Okay, so here at t equals 0, where the latent dimensions are randomly sampled. Here at t equal 100 steps, and here t equal 1000 steps. Okay, and you can see what we can see here is that certain latent dimensions are more activated than the others, which can be explained by the fact that these components correspond to the universal components, as we will see later with the different inference configuration, where we see actually the exact impact of these components on the learning process. Okay, we'll dig to it. So here we can see simply that throughout the process there are some latent components that are more activated than the others because of the decomposition process that is carried at the local level and the conciliation process that reinforce these components, these latent components that are more activated than the others. Okay. In this part, we study the performances of the proposed model compared to the state-of-the-art approaches like deep conv-LSTM and deep sense. And this table compares the recognition performances obtained with the baselines and the considered representative data sets. As shown here, our proposed approach performs well on the three considered data sets overall. And in particular, we are able to improve the recognition performances on the SHL dataset with approximately 5%, 5 points. Overall, our approach on all the considered datasets leads to a noticeable improvement, and noticeably on the SHL dataset, as you can see here. This leads us to the more interesting part, as we have to investigate the behavior here of the different components in different inference configurations. First, we assess the usefulness of the separated components, so the universal components on the one hand and the position-specific components on the other hand. So we use them in a traditional discriminative setting as inputs to a classic dense layer. So we can see the recognition results with the different representations learned at a local level by each learner with and without conciliation phase. Okay, so for example, these highlighted classification results are obtained using the universal components learned by the hand-specific learner as inputs to the dense layer, while these are obtained using the hand-specific components as inputs. So universal components on the one hand, hand-specific components on the other hand, okay, as inputs. So as we saw, there are improvement with the conciliation phase. So the conciliation phase is important, and what we can see is that also the universal components are able to provide, in some cases, better results than position-specific components. Okay, so it depends on the activity action. Here we can see also the confusion matrices that combine between the universal components of the central learner and the specific components. So for example, combining ZA, so the universal components, and Z torso, the torso specific components. Okay, and you can see here that some activities do not give good results. There are other specific issues with these activities, but beyond that, these types of activities require more featured or not basic, maybe suitable combinations of these components. So this is what we will see after this. So here, what we tried is, rather than using basic inference configurations, so ZA alone or position-specific components alone, we combine between different positions. components, specific components of different positions, and the universal components. So, for example, here we can see illustrated the results obtained with other combinations of inference than those previously used. And for example, here we highlight an inference configuration where the activity subway is inferred using the combination of the universal components, the A, the hand-specific components, the HA, and the torso-specific components, ZT. Okay, and interestingly, we can see an improvement in recognition performances compared to the basic configurations, and this gives more featured and a fine-grained mastering of the learning process and the inference process, actually. So to sum up, what we saw together is that smart sensors in various positions of the space provide rich perspectives and contribute in different ways to the learning process. However, the information conveyed by these different perspectives or views are not necessarily of the same nature. And in standard learning configuration, this noise is unfortunately not without consequences. So this is what we call the sensor's bias, the sensor's position bias, okay? So, and we saw together also one approach that tries to abstract away or circumvent the impact of this bias by actually decomposing the sensory signals into different parts corresponding to the different types of information that are conveyed by these perspectives. And the results, as we saw, are encouraging and open up perspectives regarding the development of more featured approach to decompose these information and to deal with other forms of biases that stem in these kinds of deployments and sensor and IoT deployments in particular. Well, many thanks for your attention, and don't hesitate to ask questions and leave an email at the contact that you can see here. So thank you very much, and happy to hear from you. Bye. Thank you.